Hello everyone, welcome to this video. In this video, we will focus on creating a submarine grid to suit its flow physics. The usage of unmanned water vehicles and submarines for mapping, intelligence and other applications increased significantly over the time. Until recently, the design process mostly relied on the traditional methods. With the recent developments in high-speed computing and robust algorithms, CFD is rapidly emerging as a reliable and economical design tool. Unlike ships, maneuvering the submarine is challenging due to its motion in 6 degrees of freedom. It requires a complex set of control surfaces such as sail and stern appendages to meet the demands. As the number of control surfaces increases, the complexity of the flow field also increases due to the interaction of one control surface with another. This complex flow field in turn demands a good refined grid for accurate and reliable results. Let's look into the details of the regions where we need to refine the grid. First, we will start with the domain. In general, the domain is chosen based on the type of simulation. Of the various tests available, captive model testing is considered as the best method, which is now being virtually simulated with CFD. Under captive model testing, there are different tests for different motions, such as straight line towing test, rotating arm test, and planar motion mechanism test. Each test demands a different domain. For example, a cylindrical domain is chosen for rotating arm test, whereas a box domain is preferred for a straight line towing test. And a combination of both is preferred for the planar motion mechanism test. In PMM, a cylindrical domain is chosen closer to the geometry in order to set a dynamic mesh boundary conditions with a box domain far field. Typically, all the box boundary domains are kept as far away as possible. For example, 15L for all the boundaries except the outlet, which is kept at 25L, where L is the length of the submarine. And for a cylindrical domain, the boundary is kept at 8L. Next, let's look into the flow physics. The flow phenomena changes with respect to the submarine maneuvers. For example, when the submarine is in surge motion, the flow field is simple with the wake behind the sail, stern appendages, and propeller. But when there is a yaw or sway motion, there would be a shift in wake vortices towards the leeward side of the sail, stern appendages, and propeller. So each motion shifts the region of interest and hence the refinement regions. In this case, we will be focusing on the overall refinement. So considering the maneuvering of the submarine and the shift in wake vortices due to the traverse flow, we need to refine a wide range of 3D space around and behind the sail and stern appendages. This can be done by a local refinement using densifier as shown here. This would refine in all three directions one after the other without propagating it to the far field. Lastly, the boundary layer resolution, which is critically important for these RANS computations as there are large flow separations at high beta. As it can be seen in the image, vortex shedding from the sail and stern appendages interacts with the hull surface and disrupt the smooth attached flow pattern. A typical Y+ distribution on the submarine looks like as shown here. It is also observed that full resolution of boundary layer with a Y+ of less than 1 helps in getting better mesh convergence and reduces the grid uncertainty level considerably. So I have chosen a first cell spacing of 1e⁻⁻⁴ with a Y+ of 1. With these modifications, the grid is now good to be exported to any CFD solver for computation. This brings us to the end of the video. Thank you for watching. If you have any questions or you want us to post any specific tutorials, please leave your comments below or write to us on Twitter. The social media links can be found in the description. Do subscribe to the channel to get updates on new videos.